Hello and welcome to our lesson on geometrically defined vectors. So let's get started with a little bit of terminology. For instance, when we're talking about a quantity that is defined by its size or its magnitude or just a strict measurement, we're generally referring to these quantities as scalars. But sometimes a scalar amount, a size or a magnitude is not quite enough to give us full context in a situation. So for example, if I said, I'm traveling on a freeway going 60 miles per hour, you're like, cool, I know how fast you're going, but you have no idea where I'm going if I don't also give you some direction. So if I said I was going 60 miles per hour due north on the 17, you have a better idea of where that is. So if we're talking about just the size or magnitude or measurement of something, again, that's a scalar amount. But if we want to also give that magnitude or size a direction, then a quantity that possesses the magnitude and direction is going to be described by vectors. So we're going to be using vectors, again, to describe a quantity that has a size or a measurement and a direction. So it has the two components, like velocity or acceleration or force. Like force, for example, when we talk about, let's just say weight, right? If something has a weight of 50 pounds, what does that actually mean? It means there's a weight of 50 pounds gravitationally pulling us toward the ground, right? So there's a direction for a force associated with that measurement of 50 pounds. Okay, so when we're trying to depict these, there's a geometric way to do this. There's also an algebraic way to do this, which we'll talk about in the next topic. But geometrically, what we're looking at when we're depicting vectors are directed line segments. And so you see an example here of a directed line segment. Basically, what's going to happen when we're depicting a vector is we're going to start with some initial point, and that would be the end point on this directed segment that we would see. And we can also call that the tail end of the vector. And then there will be a terminal point, much like with a terminal ray for an angle. We're going to call that the head of the directed segment. And again, that's where we're going to see the arrow. So when you see this is an example of a vector. It's got a magnitude, it's got a direction, so I know it's 8 centimeters in length and a 20-degree angle from the horizontal that's here. This would be the initial point or the tail end of that directed segment, and this would be the terminal point or the head of that directed segment. Okay, so lots of circling and messing up my paper there, but if we're looking at multiple vectors at the same time, two vectors are going to be considered equal if and only if they have the same two components. So if they have the same magnitude and the same direction. The location is irrelevant. So for example, I have a vector drawn here. I have the exact same vector drawn here. We can see that the length of those two vectors is the same, that the direction is the same. If I was to put in a horizontal, there would be also a 20-degree angle here. Those two vectors are considered equal, even though one is drawn to the left of the other. Okay, so equal vectors have the same components that make a vector. Those would be magnitude and direction. All right, so let's just get a little more vocab in. So if I wanted to know the magnitude of the vector that's in this first box, the magnitude of the vector would be the measurement of the vector itself, which would be the 8 centimeters. And if I said, what's the direction? So a lot of different ways to give direction. We've seen direction given with bearing, where we start from due north, or bearing with two components like north 42 degrees east. Here we see a 20-degree angle of elevation from the horizontal. So the direction would be 20 degrees from the horizontal. Or again, we could say that that is a 20-degree angle of elevation because that's implying that it's from the horizontal. And it looks silly that this is not with this. There we go, that looks better. Okay, so the magnitude, again, that's just the size or like the length, the measure associated with the vector, and the direction is going to be depicted by some angle, okay? Or even if that angle wasn't there, we could say that this direction that it's pointing is the direction the vector is heading, okay? And we also have multiple ways to name a vector. So we have a terminal point, we have an initial point, so we can name our vector by those 2 points, and sometimes we can name it by the magnitude that we would see, the measurement that we would see above it. So in this particular case, I could call this vector x, or I could call this vector vw. Now when I'm using the two endpoints, well, the initial point and terminal point to label that vector, I want to make sure it's the initial first followed by the terminal. So if it starts at v and ends at w, it has to go in that order. Now instead of writing out the word vector, we could also say vector x like this by putting an arrow above the x, or we could say vector vw, vw like this by putting an arrow above the v and w. Now if I wanted to talk about the magnitude, we have a notation for this as well. So for the magnitude of vector x, I could say like this. We put these bars that look like absolute value almost, okay? So similar symbols but different meaning. That is the magnitude of x. Or we could say the magnitude of vw like this. So the magnitude again is the measurement of it, and then there's no direction given on this one other than it's pointing this way, so let's not worry about the direction here. Okay, so same concept. If I have this vector shown in the third box in green here, if I was to name this, I could call it vector r, or I could call it vector q and then p, initial and then terminal points, or I could use the notation. I could say vector r with an arrow above the r, or I could say vector qp with the arrow above the qp. And then if I wanted to reference the magnitude of this vector, then I would say the magnitude of the vector would be like this, the magnitude of r, or I could call it the magnitude of qp. Okay, so just some terminology there, and actually a little more terminology before I can show you where we might use some of these concepts. So what we're going to look at first is adding vectors, and most of the work that we're going to do with vectors is pretty intuitive. So adding and multiplying the way we typically are used to doing with normal numbers. Just it's the terminology that sometimes is a little strange. So the sum of two vectors is also a vector, and it has a special name. The sum of two vectors, the third vector created there, is called the resultant. It's like the resulting vector. And there are a couple ways geometrically that we can look at adding them. So if we're adding, we can add them in a way that we call head to tail. So if I wanted to add, let's say, these two vectors, a and b, and remember, I could put b over here somewhere. If I wanted to add it to a, which is over here, what I'd want to do is connect those two. So think about taking this and sliding it over to get to here. If I do this, what I want is for, when I say head to tail, the terminal side or terminal point of a to be coinciding with the initial point of b, so that I'm looking at a ending and then b beginning and landing here. If I drew in this third vector that had the same initial point as a and same terminal point as b, then that's going to represent the sum of those two vectors. And hopefully it makes sense, right? If I went this far this direction and then I went this far this direction, this is where I land. So instead of taking that long way around, I can just go straight from this point to this point. It's like the shortest distance between the two, right? And so that would be one way to visually see the sum for those two vectors. And that's what all the jargon says over here, basically. Okay, just connecting the tail end of one to the head of the other and making a third vector, which is the sum of the two. And now another way we can look at adding vectors is using what we call the parallelogram rule, which is pretty similar. So again, I have a connected to b, but notice this time they share the same initial side. So again, think about B here. I could take this and connect this way, but I don't want to use the same method here where it's it's head to tail. Here it is the two initial, sorry, my pen froze. The two initial sides coinciding or corresponding. So the parallelogram method says if you coincide the two initial points and then basically make a parallelogram out of this. So if we look here at side A, if I just duplicated that from the end of B, and then here I have side or vector B, and then I duplicate that over here, I'm making a parallelogram. So a parallelogram is your four-sided figure that has two pairs of parallel sides. So the two yellow highlighted ones would be the parallel sides, and then the two green ones would be the parallel sides. Well, the diagonal that's created in this picture is also going to represent the sum of those two vectors. And I could see, because vectors A and B are the same for both of my pictures here, how that length is the same in both pictures. So the parallelogram method is, instead of connecting head to tail, we connect the two initial points, make a parallelogram, and then the diagonal of the parallelogram becomes that sum. Okay, but both of these showing the same sort of concept. Okay, and probably this second one is used a little bit more often, but hopefully both of those are sort of making sense. Okay, now it doesn't matter the order that we add these, so if I was to switch the sides A with B and make my parallelogram that way, it's not going to matter. I'm going to end up with the same sum. So when the order that we add doesn't matter, this is true for normal addition, we say that the addition is commutative. Again, the order doesn't matter, meaning it is commutative. We can change the order and not change the problem. So like 4 plus 2 is 6. I can change it to 2 plus 4, but I still get 6. The same is going to be true with vectors. So that vector A plus vector B, or vector B plus vector A, same result either case. Okay? So addition is commutative not just for real numbers, but also for vectors. And then we have this concept of opposite vectors, which I should have mentioned in the box up in the beginning, but I'll go back to it. Opposite vectors have the same magnitude, but they go in opposite directions. And so what would happen if we were to add up two vectors that were opposites, that means same magnitude but opposite directions, is they're sort of undoing one another, and you end up with a magnitude of 0. And so the resultant of opposite vectors, the resultant of the sum of opposite vectors, is what I meant to put in there, is called the zero vector. And sometimes a vector's opposite is also referred to as its equilibriant, but I'm not so concerned with that word. I just thought I'd throw it in there. And so let me go back to this picture up in the beginning. So the first two, the red vector and the blue vector, the first two boxes here, those two vectors are equal. They have the same magnitude, that means the same basic length or measurement, and the same direction, the same angle from the horizontal. So we would say that these two are going to be equal. But if you look at the ones I have here in red and green, their magnitude is the same. Like the length of each of those, if I took a ruler out and measured them, their lengths are going to be the same, but one's going in the complete opposite direction of the other. So these two, we would say, are opposite vectors. And if I was to add these two opposites, then the magnitude would be 0. So if I went like 8 units this way and then I went 8 units that way, then I would end up with just a point, right? So if I start at a point, go this way, and then come back the same amount, I end up right there. There's no magnitude left. There's no actual vector left, just that point. So these are opposite vectors. And again, the sum of opposites is just going to end up being 0. And over here we have same magnitude, same direction, we have equal vectors. Okay, so opposite vectors, the sum here would be 0. Just to connect, down to what we were talking about below. Okay? And then it doesn't really have to do with addition, but Again, most of the operations that we'll look at with vectors are pretty intuitive, and that's true for scalar multiplication. It is intuitive. That means it should make sense just visually. So I put a little picture down here. We're not going to do a whole bunch of this. We'll do more of the actual work when we get to the algebraic look at vectors. But for now, if I gave you this vector, that's not what I wanted. Hang on. If I gave you this vector u, and I said to draw me a vector that was twice u, then the vector that's twice u would have twice the magnitude but would go in the same direction. And so that's exactly what we see happening here. There's u one time, then there's u a second time, so that full vector is twice u. Or if I said 3/2 u, that'd be like 1.5 of them. So here is one of them, and then half together, making the 3/2 u. Or take half of u, which would be half of what I see here. And then -2 times u means not only double it, but make it go in the opposite direction. So this is double the length of the u that we see there, and again, going in the opposite direction. So hopefully those things are intuitive and visually just sort of make sense. Okay, and we'll do more of that, like I said, when we get to the algebraic one, but for now, just kind of go with it. Now I want to show you some types of problems that we can solve using the concepts of vectors and some of the solving techniques we've already seen in this module. So for instance, and I put some properties of parallelograms here, which I may reference just not quite yet. So if I said to use the parallelogram rule to find the magnitude of the resultant force for the two forces shown in the figure. First, I forgot to put some units. This would be like, let's say 40 pounds of force here and maybe like 60 pounds of force here, and then a 40-degree angle in between those two forces. Okay, so no context, which makes this a little bit strange, but what we have to know is the language. Use the parallelogram rule to find the magnitude, that means like the length, or the number of pounds of force for the resultant force. So the resultant, that is the sum of the two vectors that we're seeing in our picture. And using the parallelogram methods means make a parallelogram out of this. So if I duplicated the 60 up here and duplicated the 40 over here, then I'm making a parallelogram. The diagonal of this parallelogram is the sum of those two. It is the resultant force, and that's what it's asking us to find. So I made a parallelogram by just duplicating the two forces that I was given. That's the two vectors that are already there. And the resultant force, that's the sum of those two vectors. That's the diagonal of my parallelogram. That's the one that we're trying to find. So that's going to be what's in question here. So I'm going to call it R for resultant, although you could use whatever variable makes you happy. But how are we going to solve this? So one of the helpful properties to know in a parallelogram is that the opposite angles are equal. So let me go back to this. Opposite angles in a parallelogram are equal, and also that adjacent angles are supplementary. So for example, in this picture, I don't need all of this, but just to show you. So if I have a 40-degree angle here, I'm going to have a 40-degree angle here, so those would have to be equal. And then if I have a 40-degree angle here, this angle here will be supplementary to that angle. And then also here, we would be adjacent. This would be supplementary to my 40-degree angle. So if I have 40 degrees there, I have 140 here and across from it. So adjacent angles are supplementary, opposite angles are equal, and it should make sense. Alright, so that this angle in here is supplementary to the 40 degrees. So if I took 180 and subtracted out the 40, that's where I'm getting that 140 degrees. And then in this picture, I duplicated these sides, so I know this is going to be 60 pounds up here. And so looking at the triangle that's been created, this triangle right here, what we have in the triangle, it's a little weird to think about 40 pounds and 60 pounds there, but we have those magnitudes, we have the lengths of those sides, we have the angle in between. What I have is a triangle that's guaranteed by side, angle, side. So I should be able to use the law of cosines to calculate the side opposite of that angle that's given. So let's do it. I'm just going to pick a version of the law of cosines. So let's say we had a squared equal to b squared plus c squared minus 2bc times the cosine of a. Because I have different variables, or actually only one variable in my picture, but this is the angle that we have. This would be the side opposite of that angle. And then b and c would be the other two sides that are in the picture. So what we're going to say here is that instead of a, we have an r, and actually it's a vector in this picture. So I'm looking for the magnitude of that vector. So instead of calling it a, I'm going to call it the magnitude of r squared. That has to equal to b and c, that's those other two side lengths. So we can just say 40 squared and 60 squared, and I don't have to put the magnitude symbol in there because 40 is the magnitude and 60 is the magnitude. And then minus 2 times, again, 40 and 60. And then we're going to multiply by the cosine of the angle that we had, which was 140 degrees. Which means the magnitude of r, that's the thing I'm looking for here, the magnitude of that resultant force is going to be the square root of all that stuff that I just wrote. So the square root of 40 squared plus 60 squared minus 2 times 40 and 60 times the cosine of 140 degrees. And so we go into the calculator just one time to find the magnitude of our resultant force, approximately equal to, lucky for you, I did this, the first one up here, I typed in all of that stuff under the square root and got about 94.23-ish. So about 94.23, and that would be pounds of force in this case. Okay, so hopefully that's not too terrible. Understanding some of the terminology to get the picture, but then solving using something we already know. And this next one's going to be very similar. So we have two forces of 15 and 22 newtons acting on a point in the plane. And a newton, that's just a unit of force that basically is about 0.225 pounds. But knowing that it's a unit of force means it has to be a vector. So it's got like a weight to it and a direction that it's being pulled. So there's some vector acting on, there's actually two vectors in this case acting on a point that's in a plane. One's got a force of 15, one's got a force of 22. So if I was to try to sketch this out, I have this point that's in my plane. So I'm going to make my point here. And then I have two forces. So these two forces of 15 and 22 means I have, and then it tells me there's an angle between them, 100 degrees. So I know I'm making an angle between these. So one force of 15 going like something like this, maybe. And then I have this other force like this, perhaps, at 22. And maybe this isn't drawn to scale, but it is what it is. And it says between these two forces, there is a 100-degree angle. So I'm going to put 100 degrees in between. And again, it says to find the magnitude of the resultant force. And I'm just going to make this a little smaller so it looks a little bit more to scale, although I don't know. Okay, so here it is. So again, 15 and 22 being forces means they represent vectors. We have two vectors, they're going in different directions, and I know this because there's an angle of 100 degrees between them acting on that point in the plane, which I just drew as a red point, but maybe I can call that point P. Alright, so the resultant force would be the sum of these two vectors, and because they are connected with their initial points, again, I would use the parallelogram method here. So I'm going to duplicate 22, and I'm going to duplicate 15 to make this parallelogram. Not great, but you get the idea. Then the diagonal is going to be that resultant force. So the diagonal, let me make another color here. How about black? The resultant force is going to be this piece in here, and let me use my draw tool. That was terrible. There we go, something like this. Okay, so this is the picture. Again, The adjacent angles have to be supplementary, so if there's a 100-degree angle here, that means that this angle adjacent to it, next to it, is going to have to be 80 degrees. And then I duplicated the 22 up here. So this is the same exact picture I see in the previous problem. I have a side, angle, side. So I have a triangle that I can solve using the law of cosines. So this triangle is guaranteed by side, angle, side. That's what tells me to use the law of cosines to solve. So again, just pick a version of the formula. I'm going to pick a squared equals b squared plus c squared minus 2bc times the cosine of a. Again, this is the resultant force that I'm looking for. Again, I'm going to call that r. That's the piece down here. That has to be a, and goes with the cosine of a. This is my angle. This is the side opposite. And then b and c are just going to be the other two pieces, the other two side lengths that are in my triangle. So I'm going to say that the magnitude of my resultant force squared is going to be equal to 15 squared plus 22 squared minus 2 times 15 times 22 times the cosine of 80 degrees, which means the magnitude of my resultant vector, again, is going to be the square root of all of that stuff. So 15 squared, 22 squared, minus 2, 15, 22, and cosine of 80. So the magnitude of my resultant vector is going to be approximately, again, I did this one already, just make sure, remember that you're in degrees. So the second one, which I have about 24.38. In this case, the 15, the 22, and the r have to be in the same unit, so that's going to be about 24.38 newtons of force. And again, those newtons are just fractions of pounds. Okay? So not too terrible. Hopefully, again, just understanding the lingo, being able to draw the picture, and then use law of cosines, which we've already been using to solve. All right, this next one gets a little tricky, so let's see. We can also use vectors to find force. So we were using it to find force in the other pictures, but a little different in this one. Let me show you. So we're going to try to find the force required to keep a 50-pound wagon from sliding down a ramp inclined at 20 degrees to the horizontal. And we're going to assume there's no friction here because you need a little bit more science to solve in that case. So find the force required to keep a 50-pound wagon from sliding down a ramp that is inclined at 20 degrees to the horizontal. So first, what does that look like? We're going to have, hopefully it makes sense, some kind of a triangular picture here where this is going to be my ramp, which means I have a wagon sitting on this ramp. Don't judge my art, okay? We've established that I can't draw. So this is going to be my wagon. It's so sad. That is sitting on this ramp. And it says that there's the ramp is inclined at 20 degrees to the horizontal. So if this is the ground here, that means the 20-degree incline is happening in between the ground and that ramp. So the question is, what's the force required to keep this 50-pound wagon from sliding down this ramp? Now, when it says that this is a 50-pound wagon, that not only is giving me a weight, it's telling me, remember, when we weigh 50, something weighs 50 pounds, that's a 50-pound gravitational force pulling to the ground, right? Pulling that mass to the ground. So I'm going to draw that in right here, straight down through the ground, and I don't know how far this is going to go. I'm just going to make it go here. So that means there's a vector, there's a force pulling on that wagon, and that force is 50 pounds. So I'm going to put that in there. Okay, 50 pounds of force. What it's asking is find the force required to keep it from sliding. Okay, find the force required to keep it from sliding. So somebody's holding the wagon with some amount of force, or something is holding the wagon with some amount of force, pulling it upwards to keep it from sliding downwards. So that's the force that I'm trying to find. Okay, so how am I going to figure out that amount of force? That's the real question, right? Now I'm just going to take this down here. Oops, not what I wanted to do. Take that same amount that I'm trying to find. I'm going to bring it down here just because it's going to be a little bit easier for me to see it. And it'd be a little tricky about this, so once you see it done, you'll understand what I'm doing. What I'm going to do next here is drop in a perpendicular to my ramp. So if I draw in this perpendicular to my ramp, let's use my draw tool so it actually looks good. Well, that wasn't even better. How about this? Okay, a little bit better. If I draw in the perpendicular to my ramp, and again, remember, this is my question down here, but the reason I put this perpendicular in is because now I have this 90-degree angle here, I have this 90-degree angle here, and I also have a 90-degree angle here, which it was already here, but just so you can see it, that establishes some information in the triangle that's going to help me solve. So let's focus on this triangle for a second. Right? In this triangle, I have two of the three angles. I have a 20-degree angle and a 90-degree angle, which means the missing angle here, oops, that's my highlighter, has to be 70 degrees. So I can put 70-degree angle here. And then these three angles make 180 degrees. So if I take away the 90 and the 70, that means that this little angle here has to be 20 degrees, which means this angle here has to be 70 degrees. It's the same triangle. This triangle here is the same triangle that I'm showing you here. Just hopefully makes sense what side of the triangle that we're trying to solve for. Okay, so now solving in this right triangle actually shouldn't be too bad because it's a right triangle, and I have the side that is well, depends on what you want to use. So let's say I wanted to use this angle. Right, this would be the adjacent side that I'm looking for. This would be the hypotenuse, which means I could just use the cosine to solve. So I could say that the cosine of my 70-degree angle is going to be equal to a ratio of the adjacent side over the hypotenuse, which was 50. And so multiplying by 50 is going to get me my answer. So A would be exactly 50 times the cosine of 70 degrees, which is going to be approximately something my calculator will give me. 50 times the cosine of 70, and that ends up being about 17.101. Let's just say about 17.1, and this is going to be pounds, just pounds of force. Okay. So I know that was probably a little tricky, and maybe you would not have figured out how to draw that on your own, but the one that you're going to see in your assignment is going to look just like this, and hopefully the picture that I created there makes sense, aside from a terrible artwork. Okay, the last problem I want to show you, look at all that space needed for nothing. Maybe I should have made my picture bigger. The last one I want to show you is really, again, something we've done before. It's just sort of a new way to look at it, or a way to connect what we've been doing with vectors to an old situation. So for instance, in number 4, it says that a ship leaves port at a bearing of 28 degrees and travels 8.2 miles. Hopefully you can see now that that's a vector. We know how far we're going. The magnitude of the vector is going to be 8.2 miles, and we know the direction. It's a bearing of 28 degrees. Then the ship turns due east and travels 4.3 miles. Again, that's a vector with a magnitude of 4.3 and a direction due east. The question is, how far is the ship from the port, and then what is the bearing from the port? So let's try to draw this out. First, let's make our port down here. The ship leaves this port, and we'll just call it point P, at a bearing of 28 degrees. So let's make the north line here. At a bearing of 28 degrees, that means 28 degrees from north. So if we started north and we rotated 28 degrees, we're going to be going something like this. And we're going to do this for 8.2 miles. So this, again, a vector with a magnitude of 8.2 miles. And here's our direction, 28 degrees, bearing of 28 degrees, so that's from due north. Okay. Then it says, at this point, it's going to turn and goes due east. So I already have my north line here. Let me just, if I went due east from this point, it's going to go this way. And if you want, you could put your north line in here too. It's going to go this way, and that's going to happen for, this a little smaller, for 4.3 miles. So this is going to be 4.3 miles here. And again, a vector with a magnitude of 4.3 and a direction due east. So then the question is, how far is the ship from the port? Well, it started here and now it lands here. How far is the ship from the port? That is the resultant vector. And now if you look at this picture, the resultant vector, this is a head to tail situation here. Basically adding these two vectors, which sounds so simple, but it's using the same work we've been using to solve. Okay, so we're looking for the missing side in the triangle. We're going to have some angles in this triangle, or at least one angle. The angle in between their side angle side would be good. So let's see if we can't get that. This is a 90-degree angle, and this is a 90-degree angle. If you focus on this triangle for a second, the three angles in this triangle make 180. If I subtract 90 and 28 from 180, what does that leave me for that third angle? So 90 minus the 28 leaves me 62 degrees for this angle here. So if this is 62 degrees, then this angle has to be 28 degrees because these three have to make 180. So that means this angle is 28 degrees plus the 90 degrees, which would be 118 degrees total in the triangle. So again, this is side angle side situation that I can use to figure out, let's call this R. Again, you can call it whatever. Here, let's use a different variable. Let's call it X this time. How far is the ship from the port? Let's call it X. So this is again a law of cosines situation. If I used, again, any version, doesn't really matter which version of the formula you use. I just tend to pick the first version. So a squared equals b squared plus c squared minus 2ac cosine, not ac, goodness, 2bc and then cosine of a. So again, a and cosine of a, that's going to be this 118 degrees and x in this case. And then the 4.3 and 8.2 will be my b and c. Okay, so I'm going to say that the magnitude of x, although I could just call it x, it's the same, but because we have the terminology now, we can use this. The magnitude of x squared is going to be equal to 8.2 squared plus 4.3 squared minus 2 times 8.2 times 4.3, and then the cosine of 118 degrees. So again, the magnitude of x is going to be the square root of all of that. And maybe I should have just done that in the step above, but that's okay. Maybe you're doing that and saving yourself some work, right? And into the calculator, we find that the magnitude of x is approximately, again, I saved us a little bit of time by putting this in the calculator, about 10.9. And in this case, we're looking at miles. And that's just 10.9 miles. If I didn't know the direction, if I just wanted to say x was 10.9 miles, actually that would be okay in this situation, but we're going to find the direction because that's the next part of the question, and then we can combine the two and call it the vector. So then here, the last part of this question, I've used all my colors. Let's go to an orange. Okay, what is the bearing from the port? So from the port, the bearing would be this whole angle here. In order to know that, I have to find this angle first, which just requires now a law of sines. It's just a law of sines problem. So I could say that, for instance, the sine of, let's call this A here. Well, actually, I called it P, so let me just move this closer. Let's say that the sine of angle P, that's what I'm going to try to find there. I'm really not looking for all of angle P, I'm looking for just that little portion, so hopefully that makes sense. The sine of the angle P that I'm looking for over the side opposite of P would be 4.3. That's going to be equal to the sine of the 118 degree angle and the side length we just found, which is 10.9. And I'm going to run out of space, so let me just move this. And now I'm going to move this. Don't you wish you could do this, right? When you run out of space, just use your technology to move stuff around. No, you just run out of space. I'm sorry. Okay, so if I want to solve for the sine of p, first I'm going to multiply both sides by 4.3. So the sine of p is going to be 4.3 times the sine of 118 degrees divided by 10.9. And then I'm going to have to take the inverse sine. So p is going to be the inverse sine of this fraction. And that means p will be approximately something we get from the calculator, and I think I did this one too, yeah. So I end up with about 20.38, let's just say about 20.4 degrees. Now remember that 20.4 is just this little piece in here, 20.4 degrees. So the actual bearing from port is that total angle. So from port, the bearing is going to be 28 degrees plus the 20.4 degrees, which makes it 48.4 degrees. So that would be the answer to the second part of this. And then again, just to mention on this first one, if you did not use the magnitude of x and you just called it x, it would be okay, because in this situation you are just solving for the length. But because that length has the direction, then we can call it a vector with the magnitude, then the notation is okay. So either way, if you didn't use it, I'd be fine, as long as you understand how they're definitely connected, okay? So we did it. We've seen some new approaches here using the vectors and seen how the vectors apply to some of our old stuff as well. Hopefully you have enough to get going on your assignment. As always, if you need some help, then just let me know. Until next time, take care.